Yezhou Yang, who's an assistant professor at joining us from Arizona State University. He did his PhD and postdoc before that at the University of Maryland, and so where he does a lot of work in computer vision, but also thinking about a lot of the issues that show up in applications involving robots, as well as language and interactions with humans. And so he's going to be telling us about some of these directions today. So without further ado, Yezhou, please tell us more about your work.
Thank you, Eric. It's my pleasure to be able to give this presentation here at UCI AI. We're going to talk about our recent, especially this 4 or 5 years I started at ASU working on visual recognition beyond appearances. So to give everyone a kind of overlay about myself, starting from my undergraduate years, I have already been working on vision, visual recognition domains, and application areas that we're attending to is trying to apply visual recognition to enable intelligent agents to perform certain tasks, or sometimes you can call it robotic tasks. And between these two, there is a gap. And this gap is what we've been focusing on at Arizona State, and also started a bit longer before I joined ASU. We call it visual recognition beyond appearances. Now you may wonder, what is visual recognition beyond appearances? Let me motivate it with, oh, by the way, since very recently I joined the Institute of Automated Mobility here at Arizona, we start to attend to autonomous driving problems a little bit as well, considered as robotics. Now, what is visual recognition beyond appearances? Let me motivate it with a piece of novel from my favorite novelist, Italo Calvino. In his book, Invisible Cities, he describes such a city. The city is called Despina, and this city is an imagined city, but it basically locates between oceans and deserts, just like Irvine and LA. And what happens is when the people traveling in the desert for long days, they see the city, they see ships. And when the people actually sailing in the oceans for long times, they see exactly city as camels. So the point really is the same kind of appearances, where's your different knowledges, different prior experience, and the stage you are for the active agent, for the intelligent agent, you discern different concepts from the same appearance. So what exactly is the problem if we ground it into computer science terms? I started my training in computer vision, right? So in computer vision, there's a whole classic literature dealing with camera geometry, dealing with normal flow, the optical flow, dealing with SLAMs. And all these literatures, we call it classic vision problems based on physical constraints, such as constraints in epipolar geometry. I know the audience is here mainly from AI and machine learning. I didn't mean to bore you, but essentially the idea is to introduce those physical constraints, that is either hard or soft constraints, imposed onto the learning problem that we can improve the model training, the model learning, the performance, such as epipolar constraint, normal flow constraint, in SLAM, there's a loop closure constraint. Now delving into semantic vision, or we call it cognitive vision, things getting a little bit vague. And this vagueness makes it hard to mathematically formulate the constraints. For example, if I give you this image and ask you to recognize, what do you see? You may say, okay, it's a duck, or maybe it's a rabbit. Now, if I put context into it, you'll see, okay, now it's a duck, it's about to eat the bread. And then you switch the context, now you perceive rabbit about to eat the carrot, right? The same appearance, the same contours, with different contexts, you perceive different things. And we call it context matters. Again, what context matters can be formulated as mathematical constraints. It's fairly blurred, it's fairly vague. Moving on, if I give you this image and ask you to recognize what you see, you may say, okay, it's lens, right? So obvious. But if you put linguistic context around, it's from Amazon, and now you realize it's actually a map, right? A map in lens shape. So if you attach a label on it, you shouldn't attach lens, you shouldn't attach a mark. Now, the linguistic context matters, how to model that. that's also problematic. Even in pure vision domain, we know there is this VQA challenge going on for years. And I was leaving Montreal one day, and after giving a talk at New Rips, I saw these 3 people waiting for buses. Now, with the state-of-the-art vision algorithms, I wouldn't be surprised the system will be able to recognize 1 person, 2nd person, 3rd person. The real question is, how can you tell the 3rd person is actually a statue or a performance artist, right? With the background knowledge, if you were a student from McGill University, you know that it's a statue commemorating the passing of Steve Jobs. But without that kind of background knowledge, purely from the appearance, it's really hard to tell whether there are 2 people waiting for the bus or 3 people. Let alone in real world applications such as autonomous driving, a cardboard reflected from the window sometimes can be easily detected as a human being in this case, right? There's all these unsolved problems ongoing. How to formulate the semantic constraints and how to incorporate them into model learning. I would like to argue the root of such a problem is really the formulation of visual recognition in the current field, right? The current field typically model visual recognition as a pattern matching problem with the following definition. It's a cognitive process that involves identification of a visible category, let's say human, face, apple, cat, etc., from previous encounters. And previous encounters is AKA training data or labeled training data. However, visual recognition as it is not only just identify visible category, but also identify visible concept, and not only from previous encounters, but also from knowledge. Here, concept could be a kind of knowledge stored in concepts, the way they are being used in agents' cognitive processes, their format, their acquisition, and so on. I'm not the one coming up with all these ideas. There was a book written by Edward Moultrie from Canada, and all over this book basically stating categories are not concepts, thus pattern matching are not cognitive vision. Now, with all these good ideas, how can we move on, right? In this environment of AI, we need benchmarking tasks to validate our ideas. So before we move on, let me go over the benchmarking tasks that we're focusing on to show that our ideas actually is legit and validated. So the first set of problems we do is so-called image captioning, that you are given an image and output is a natural language sentences describing these images. And it can be extended into video captioning as well, where you got a video, a clip as input, and the output is natural language sentences in multiple languages as well. And from David Perek's group, there is this VQA challenge. I think many of you guys probably are familiar with this challenge. You are given an image, you're given a question in natural language form as well, and the system is supposed to give out an answer that is human readable, human understandable in natural language as well. More recently, we're diving into the land of visual navigation. Now you can actually put the control signal into the equation as well. There are also large benchmarking data sets such as how 3D AI Tucson, room to room, being available, diligently compiled by the community for us to use. Not only from the public available data set, we also propose our own tasks. I'm going to quickly go over some of the tasks such as the image puzzles, V2C, video to common sense, and more recently we have a public available challenge called visual linguistic QA that enforce the question needs to be answered by understanding both the image and the text pieces recently being available in on this link as well. So all these challenges enable us to test our ideas moving on. Now, what are the solutions? At the very beginning, tracing back to 2011, we did almost the first image captioning work. In 2011 EMNLP, we call it telling a story from the images. Here you take the images and then you just simply mine the contextual information, such as knife is typically collocated with cut, so on, you can give out reasonable kind of human readable description already. And this information can basically enforce or pose some kind of naive semantic constraints into predictions that making action recognition better as well. That's about 10 years ago. Then after I joined ASU, we started to model the relationship between the object entities using a structured representation called scene description graphs. And the scene description graphs are essentially explicit knowledge representations that retrieve additional information from existing corpus, such as WordNet, ConceptNet, to supplement things that you cannot directly perceive from images. And we got decent success at that time, tracing back to around 2016. Some of the relatively smaller benchmarks, our method can gain higher captioning performance at that time, including retrieval as well. Of course, when the data set getting larger, such as the COCO, end-to-end direct trainable methodology without relying on explicit knowledge actually perform better. I'll tell you guys about the reasons later, but the whole idea is to improve visual recognition systems that can infer additional things using a large explicit knowledge corpus and posing them as semantic constraints. There are actually a couple good parts that we observe that such a way helps the system to perform better. First of all, explicit knowledge representations is fairly compatible with explicit reasoning, such as PSL, probabilistic soft logic reasoning engines, over multiple knowledge resources. So all different knowledge resources just contribute predicates, then we can essentially optimize over multiple of them and get the best answers. And more interestingly, explicit knowledge decoding yields a kind of explanation for end users and enables explainable AI that was presented in AAAI 19. We call it explicit reasoning for visual question answering. And the interesting phenomenon is whenever our system gives out an answer to the visual question, a visual question, not only just give out the final result, but being able to essentially give out a few evidences. If you guys can see the cursor here. So the evidences are essentially being represented as explicit knowledge triplets and showing why our system believes it's a toilet, because there's a bunch of evidences can be provided to the end users. However, at that time, we also observe quite significant limitations, and which some of them are actually fairly obvious. For example, even with the reasoning engines such as PSL, the lingering inconsistencies among multiple knowledge resources will hurt our overall performance. We'll show you guys how it hurt later. And there is a high fidelity requirement and low error tolerance towards knowledge sources, which also limit the performance of such kind of systems. Most importantly, it's fairly computationally expensive. Even with accelerated and approximate PSL, our inferencing time is still comparatively much higher or much slower than end-to-end approaches. In our ICHKAI 19 survey paper, we described the pros and cons of explicit knowledge in visual recognition. And here we're showing a small example that with those explicit knowledge guided VQA, we gain some performance over certain categories of visual questions, but for other categories, actually the performance hurt. Now, at that time, we ask ourselves, what next? We're apparently hitting a kind of upper bound. By the way, let me summarize this work. It's mainly led by my first PhD student, Solmak Adia, tracing back to 2016 and getting to image understanding with scene description graph, and AAAI, he did explicit reasoning and knowledge reasoning for image puzzles and a survey paper. Now he is at Microsoft Research India. Okay, so what's next? About 2 years ago, we start to play around with the sorter systems that doing VQA. And even imagine you are given this image to the system and you ask the system, is the plate gray? The system actually can confidently output yes. And as a human being, I'm observing this performance, I may think, okay, some kind of intelligence is showing here, right? That there is actually a quite complicated thing, and there's also all the objects that is covering the grain plate, but the system can actually confidently answer the question correctly. Now you may wonder, how about, let me just simply negate the question. Is the plate not gray? Now you realize, okay, the system, the SOTA system at that time also gives out yes, with less confidence, but also a strong yes to this question as well. Now as a human being, okay, I probably will give up believing the system is intelligent at that time. This is what our observation at that time, basically current VQA models seems cannot comprehend fairly basic logic connections such as negation, conjunction, and disjunction. And how to solve this? We provide a so-called explicit knowledge distillation with a way that we do data re-engineering to improve VQA robustness. Now I just showed the negation case. More importantly, there's also logical compositions that does not being handled well by the current systems at all. For example, if the ground truth is there a beer is yes, is the man wearing shoes? And if I put logical composition, multiple logical compositions to compose a new question, is there a beer and is the man not wearing shoes? The answer should be yes by purely doing logical inference, but typically the system fails at those cases as well. So in order to tackle this challenge, we start to augment the data, and not only just doing pure augmentation, we want to also introduce a new semantic constraint after this augmentation of the language data. The first augmentation we tried is definitely the logically composed questions. So in a sense that if we taking care only the yes and no questions from VQA data set, we can propose and connect the ground truth question and answer pairs into new pairs that comes up with all different kinds of logical connectors and negation, conjunction, and disjunction. Some of the examples we're showing here, for example, if there's a question, is this an area near the city? We can say and simply negate it, is this area not near the city, right? The answer should be no. And those answers are essentially also automatically given because they are following this logic constraint. And we come up with the first augmented set called VQA compose, composing 10 different variations of propositional formulas. And these propositional formulas basically dictate their answer following the logical operations. And we didn't stop there. There is a benefit of using VQA is VQA images are mainly coming from MS COCO dataset, and MS COCO dataset is well annotated dataset. With that annotation, we can essentially even supplement yes and no questions with new cases. In such a way, we create questions about objects by replacing an object word with another object word, such that it results in a change in the answer as well. And then we logically combine such questions to get even a larger training data. And in this case, we're showing an example. The image contains a person, a cup, a cell phone, and two captions are provided from MS COCO. And using this, we create additional questions, B, and this B is which is about an object, and C, which is from the caption, and logically combine the original questions with this to create this VQA supplement data set. Now, with this newly augmented, semantically augmented data, we need a model. And in this model, we decompose the challenge into multiple steps. First of all, there is definitely a question attention model a cross-model feature encoder first, and then a question attention model. And then we incorporate a logic attention model that detects the presence of the logical connectives. And then these modules are being fed into a so-called thread-chat compatibility loss. And this thread-chat compatibility loss pose a new semantic constraint that we can use to predict the final answer and train the model with better supervision. And to go into a little bit about this compatibility loss, it's a loss that is being introduced tracing back to 1930s. It's basically provide upper and lower bounds for probabilities of logical combinations, right? In our case, since all of our questions and answers are logical propositions, we can enforce them to obey these inequalities. And in such a way, we basically introduce a new semantic constraint in this case and post them into the training of the model. Of course, we also provide a baseline solution, basically semantic parse the sentences and decompose them into single questions and then throw them into VQA models and get the answer and then logically combine them. We show that this way is actually performing less robust than end-to-end training using our newly augmented data with our semantic constraint loss as well. Now here we show a little bit summary of the performance, system performance. With the original VQA data, the state-of-the-art system can achieve around 88.2 performance. And with our LOL, also we call it under the lens of logic, we do see a little bit performance drop. However, if we compose VQA compose data on the previous trained models, the performance significantly drop, right? Showing that models are not being able to understand those basic logical connectors at its purest form. And if we put it on VQA supplement, the same kind of observation shows up as well. However, with our system, we can still maintain a good, reasonably high performance on yes and no questions on VQA. In the next few slides, I'm going to show the experimental results. The major message is with the augmentation plus the semantic constraint, our system can outperform other baseline systems on VQA V2 data set, especially achieving the improvements on all the validation data, including VQA comp and VQA supplement. Comp is the VQA compose. Also, we test the system, how robust they are to compositional from single to multiple operands, right? So you can say A and B or C, negative D. And we also try to see if the system is robust to commutative compositions. So A and B should be exactly equal to B and A. A or B, it should be equal to B or A as well. And we do observe our models obey those properties as well. You may wonder how many logical samples are needed to train good robustness towards logical connectors in VQA, and we observe at least around 100K samples are needed that before the models can achieve a level of robustness to VQA compose and supplement our new data. All right. And we also did validation experiments to increase the number of operands and test our system, and showing that our system is consistently outperforming the baseline system as well. And at the end, we tested our system on VQA test set and showing improvement as well. So I didn't delve into all the details of this this paper. For details, the audience refer to our published paper. There's actually many more interesting phenomena we discover by testing all kinds of combinations of data, training data, approach, whether apply attention, not apply attention, extra. So we observe a simple logical connections can already make VQA models more robust. Actually, robustness in VQA has become a fairly active research area within the past few years. A lot of new challenges and benchmarks being established, such as VQA CP in generalization with respect to distributional shift. In CVPR 2020, EMU 2019 tackles the robustness to entailed problems, ACL 2019 robustness to implied questions, and CVPR 2019 using cycle consistency for rephrased questions. Our VQA LLL basically adds on a new dimension to the research of this area by training models to robust to logical transformations of questions as well. Now, we do see that data reengineering or semantic augmentation using logical connectors can improve VQA model robustness. The fairly natural extension that we did is, can we do not only linguistic reengineering, how about image reengineering to improve model robustness? Many of you guys probably are familiar with the VQA CP data based on the observation that models are typically relying on those spurious linguistic bias, such as bananas are always yellow, since most of the training data is dictating bananas are yellow, and without even taking the image as input. So this leads to the VQA CP challenge proposed by David Parek's groups as well, showing that, for example, even whenever you ask what sport questions, the dominating sports are either tennis or baseball in the training data. Essentially, the distribution of the answer per question type in such a case is not balanced. And thus, the VQA-CP is provided in a way that the distribution of those answers are designed to be different in the training set and test set. In such a case, those simple spurious linguistic bias cannot be directly applied to answer a question or directly adopted or exploited by the system to answer questions. Along this spirit, we introduce our VQA mutant. A mutant is basically a continuation of LOL, but not only we are semantically augmenting the questions, we can also semantically augment the images using a couple of image processing techniques. So the goal is to generate perceptually similar, yes, semantically dissimilar samples to train or to fine-tune VQA models. More specifically, each of the mutation of the inputs, question and answers, question and images, that being exposed to VQA model is being mutated in the following way. We can do a mutation where the star here is indicating the image mutation images, and that will lead a new answer X star as well. Or you can do mutations on questions as well, and leads to X star answers as well. And then the image mutations includes removal of objects, morphing of object colors, extra, and the question mutations, including word masking, word substitution, and negation. Now we're showing a few examples of the new data, mutant data we augmented. Essentially, we can use in painting to get rid of the person. Thus, the question, how many people are there, are coming from a big, altered from 2, the answer altered from 2 to 1. The same can be applied to alter the color of the objects. In a sense, what color is the racehorse is from brown, the original answer, to gray, right? With this way, we can essentially compose a new data set, and this augmented data set is with both language and image mutations. And with this data, we start to incorporate a new semantic constraint. Before I get into describe the semantic constraint, let me acknowledge the backbone models we use. We use the up-down models from VQA 2017 challenge and LXMERT, which is considered as the state of the art at that time in 2019, the best performing one in VQA challenge. Now, we first got a concept that we use. It's called type exposure. We basically train the model to identify the question type and learn which answers can be valid for each question type, irrespective to their frequency of occurrences. And then we apply those traditional VQA laws. And this traditional VQA laws is nothing but a softmax over the ground truth, comparing the ground truth with the generated answer and pose the supervised signal back to the model training. More interestingly, we also try to pose a projection loss. Here is the NCE loss to project the answer from before the mutation or after mutation onto the same manifold. And by doing those projections, we can, in this way, impose a new semantic constraint called pairwise consistency. Pairwise consistency, in its fairly naive description, is basically trying to enforce the distance between predictions for mutant samples and original samples must be consistent with the distance between true answers for mutant and original samples. To showing that on the overall system, basically we have a type exposure module to relate answers to question types. At the same time, we use traditional VQA laws plus a projection loss to project the encoded signal onto the projection manifold before and after mutation. And then we add on a pairwise consistency loss such that their distance are enforced to be similar. In order to show, for example, the distance before the mutation, there were 3 ships. And after mutation, there's 0 ships. Then the distance between Z, the vector here before mutation and after mutation should be consistent between their ground truth distance before mutation and after mutation. So by this way, we essentially can impose a semantic constraint into the training. And with that, we do observe performance boost, especially on VQA CP, changing prior data set using our augmented data plus newly imposed constraint. We're achieving around 70% on all the testing cases on VQA CP version 2 test data. And we also did experiments showing what kind of the mutant having what kind of influence on the final effects, especially testing our best models when only trained with image mutations, question mutations, as well as both types of mutations as well. As you can see, all the kinds of different mutations improve the performance on the VQA CP challenge overall. One of the interesting phenomena that I want to bring to the audiences here today is we also did and apply a so-called debiasing technology. Here is LMH. LMH used the mean model in combination with the bias-only model trained only with the question without the image to make the model robust to linguistic priors. After applying the debiasing model, debiasing layer, we actually observe a performance drop, which indicate that debiasing is essentially removing linguistic priors from our augmented data, VQA mutant, that are not spurious. Of course, this is still a pure speculation, but that's indicating that our original augmented data actually contains more language priors that are actually helpful for learning the task instead of being spurious. The way you look at this slide is you turn your head 90 degrees, since everyone is working from home. We are showing that on the very recent VQA CP challenge leaderboard, our 2 versions of Mutant are currently still holding the first place. All right, so we talked about using linguistic augmentation as well as image augmentation. We can improve VQA robustness. And some of the arguments that we got is, isn't it just a simple data augmentation paradigm? We would like to argue that mutations are not, LOL and mutant are not direct data augmentation, because we essentially form a design of semantic constraints or regularizations actually can be utilized to help leveraging a pair of related inputs. So it's not just simply augmenting the input data or the training data, but at the same time introduce a form of constraint and regularization to enforce the model to follow or to cope with certain design constraints. And similar work, such as SIM-CLR or mix in image classification already shows that carefully designed input manipulation can benefit generalization performance in image classification and vision tasks already. This part of the work is led by my PhD student, Tejas. He is currently in his third year only, starting from VQA LOL, then we get into Mutant. We also developed a visual linguistic QA challenge. And more recently, he got into robustness training, attribute guided adversarial training. And we also think adversarial training might be the way to move on to deal with all the language bias, all the changing bias, and all the, and to incorporate semantic augmentation into the training paradigm. Let me also acknowledge Pratya Banerjee, an NLP PhD student at ASU. We close collaborate with him for this line of work as well. Now, the next question we want to ask ourselves is, there is also explicit kind of common sense for, in a common sense form, you can augment or you can impose semantic constraints in visual recognition or visual recognition systems as well. And in this case, we utilize the recent knowledge atlas proposed by Alan AI called Atomic to augment video captioning data to be with cause, attribute, and effect. So due to the time, I will basically go over this new data with you guys quickly. And I really would like to introduce data because we did get very interesting annotations, and that could serve a benchmark data set to validate a system whether they can indeed infer from appearance to hidden entities as well. For example, in this case, we are given a video clip, right? A group of persons dancing in a room. The way a human understands it is not only the current event, the event is going on, but also who are the agent or why this agent doing this, so-called cause. And what can be the effect of the activity, which is the effect. And also a bunch of attributes, what are the characteristics of the agent as well. With this spirit, we create the video to common sense data set presented in NLP 2020. We incorporate video sources from MSR VTT, which contains around 10K videos, each has 10 to 30 seconds, and use natural language processing tools to augment it with common sense knowledge that is retrieved from Alan AI Atomic dataset. And let me quickly go through the pipeline of the augmentation. We essentially first use bird ranking to pick the top a few candidates that can be considered as a candidate to augment a specific video. And then we send it to Amazon Turkers to ask them to annotate which one among them, which one among those courses makes the perfect sense for this video right now. And for the ones that all of the automatically generated or suggested courses are not, or effects or attributes are not correct with the specific video, we also ask human being to annotate if needed. So with that, we get the video to common sense data set in a sense that we can augment a caption from the MSR VTT with intention and effect and attribute. And one interesting thing with those augmentation, we can even enable a more challenging VQA task on the V2C data set, in a sense that with conventional video QA, we may only answer who is fighting and the soldier is fighting given such a clip. But with augmented data, we can essentially augment it and answer questions such as, or pose questions such as, what is the intention of the person on the left? And the intention might be to defeat the enemy, to protect the country, etc. So in total, we also get around 37K questions to be posed to test systems, to test system whether they can infer underlying intent, underlying effect, and underlying attributes of the event from the videos. Here are some examples from the V2C VQA data. Okay, V2C VQA data, and including intention, effect, attribute, and we can also permute different ways of posing the questions and getting different answers as ground truths as well. All right, the model, baseline model we adopt is a transformer model, and we do observe the baseline model can perform certain, to a certain extent, success at doing V2C completion or the caption generation. And we also did human validation for the V2C completion and generation results. Some of the qualitative results are showing here. For example, in this video, where you're seeing a person is training for soccer, the generated caption is not only just a man is playing a soccer game like previously, but it's actually accompanied with the course. He wants to know how to play soccer, and he will cautiously dribble the ball. By the way, those generations also condition on the image or the image features. So those generations are actually also not just template retrieval from the knowledge base. And the last is about the attribute the man is seeing as is used as in this case. All right, so there are also a bit more about semantic constraint, posing semantic constraints, dealing with counterfactual cases, doing fine-grained visual textual alignment, and even doing self-supervised knowledge distillation. I don't have time to go over them today here, but that could make into my next talk. There's a collaboration with Professor Charles Fox here at, we did modularized textual grounding for counterfactual resilience in CVPR 2019. And in CCV 2020, we did visual textual alignment. So at the fine-grained level to align text with image input to better facilitate text-based person retrieval. And more recently, and Jacob leads this work at doing self-supervised distillation for visual representation to appear at ICLR 2021. To summarize, Jacob is a fourth-year PhD at my group, and he starts with textual grounding, get into fine-grained alignment and V2C, and more recently get into self-supervised knowledge distillation. And we also believe self-supervised way might also be a potential way to move forward from dataset era to post-dataset era, which I would like to summarize later as well. Let me see how much time I have. Do I still have like 5 to 10 minutes, Eric? If I do, I can.
Yeah, you have maybe 7 minutes or so.
Okay, thank you. Thank you. Yeah, I'm trying to go over all the slides that I prepared. Okay, so right now, we talked about work that we did in vision and language, especially doing things that we want to infer things beyond the pure appearance. What is the overall goal? I think what would I like to propose following this line of research is a common semantic augmentation paradigm. So if you think in the following way, right? A typical vision and language task or a task with multimodality inputs, such as vision, images, or videos. And then you have language text. And there is some form of mapping between them that you want to learn. And in VQA, there is also an output, such as an answer. Then you form basically a triangle of relationships you want to learn between them using machine learning tools. Now, what essentially we are doing is we pose a function to augment or to semantically change the visual space. And we pose another function to semantically change the language space. And combining them both, by the way, we can establish a new relationship between them as well. Now, by combining them, we basically can also output a new kind of answer that, given the video or vision or image augmentation and language space augmentation together. Here, F is a kind of computer vision algorithm, such as in painting, morphing, so on and so on. It's a kind of trained AI, and G is a form of NLP process, such as semantic parsing, entity recognition, entity replacement, and so on. Now, we are basically trying to close such a loop by saying whether we can train an AI, whether it's a vision algorithm or an NLP algorithm or both, to augment or to generate data to train another AI, in this case, for a holistic view of the space that all the kind of robustness in vision and language pre-trained models. There is a very recent work from Microsoft AI research that I recommend the interested audiences to refer to. Most importantly, with those augmentation, mutation, data alteration, we can force or we can pose new semantic constraints onto the model themselves. And those semantic constraints can be incorporated into model training to make the model more robust, better performance, faster inference, so on and so on. All right, so with that being said, we haven't got a chance to talk about putting the agents into the formula, because the concept really is not only just about the category, and also not only about the knowledge stored in the concept, it's also in the agent's eyes. So let me quickly give out our flavor that we are doing at ASU APG about incorporating in the concept of agents in vision and language research as well. The task currently we are focusing on is so-called active object perceiver. You are given a target object to the robot, and the robot navigating in the room. Here is a top-down view of the room to localize the object without pre-assumed maps and only taking first-person view image as input. The underlying idea is really the same, right? You see the same image, and with different goals, the action are going to be different. Thus, an agent needs to infer not directly from the appearance of the image, appearance of the current view, but also incorporate its underlying states, underlying goal to give out the right action to perform. Over the years, we have been testing on using recognition as a module to do object search, incorporate with a reinforcement learning algorithm. And we also show that a generalizable policy can be learned if we incorporate explicit knowledge such as depths and semantic segmentation masks as well. And more recently, we start to decompose the task into 2 layers. The lower layer deals with the low-level actions. The upper layer is reasoning between the high-level concepts such as sofa is close to TV, TV is typically in a living room. With that decomposition, we can enable a goal modeling. Here we have a very recent work under review. We call it goal relational graphs. And this goal relational graph is a Bayesian relationship that during the training, you start to build the relationship between the objects, and those relationships as represented as a graph can be utilized in generation time or in action performing time to achieve the ultimate goal faster with less exploration time. And in this way, we sort of also imposing new semantic constraints. Here, the semantic constraints is not imposing on, let's say, answer a visual question, but it's imposed to train a better policy for object search. I'll skip the video demo. And this line of work is led by my student Shane. She is graduating fairly soon. Her lineage of research are essentially focusing on object search, starting from object perceiver, generalizable approaching policies, and more recently getting into hierarchical planning as well as goal relational graphs as well. Briefly, we also have a line of work, which I can only give you guys a flavor, that we're basically saying that a DIM model can be adaptively updated and distill its knowledge into a shallow model that enable processing onto edge devices. So in such a way, we call it Argos. It's a planning module that can plan all the object parts or the object proposals and actively and adaptively put them into a smaller model. And those smaller models are implemented on boards such as FPGA and smaller NVIDIA boards as well. And we are showing that the frame rate is higher, the energy cost is much lower, etc. This is led by my student, Mohammed Fahadi, and the Argos architecture is going to be released fairly soon. All right, so with the remaining a few minutes, I would like to wrap up today's talk with a few thoughts. First of all, one of the talks that really inspired me this year is from ICML 20 plenary talk by A.E. Frost, imagining a post-dataset era, right? How we are moving into an era of machine learning that a dataset becomes dynamic, dataset becomes adaptive, and the dataset itself is not the only starting point for research. And to cope with them, we propose and we present, and we're also doing research in semantic augmentation, such as LOL, Mutant, V2C, etc., as a general tool to augment VNL challenges. And actually not only for VQA, any kind of new vision and language challenges, new challenges being proposed, we want to provide such an augmentation tool set that they can be directly applied onto the annotated data to generate new set of data for robust model training and to generate a new set of data that those semantic constraints are essentially encoded in the generation process as well. And there is also kind of a trend going on in vision and language research. I don't want to generalize it too much, but probably it's also happening in other AI and machine learning fields as well. For example, we're seeing existing new challenges, fairly exciting new challenges, and performance gets saturated fairly soon. And then people start to recognize repeating flaws. And those repeating flaws are not specifically for this task. For example, language bias. Language bias has been proposed in NLP domain in pure language tasks over and over again. But here, we are basically without even, sometimes you can even call it re-bring it up, right? Bring it up to a new task showing that this language bias also exists. Then you see the performance resaturation again. This loop going on and not really bringing anything new to the field outside of this focused domain. Here in vision and language, we observe this cycles in captioning, then VQA, right? Then and all derivatives of VQA. Then more recently, VLN, visual language navigation, and even more recently, VCR, visual common sense reasoning. And there is a very recent AAAI paper coming out talking about that VCR task by itself, even though it's a fairly exciting task, by itself, you can solve it 75% with 75% accuracies by simply comparing the answers with the question, and those the most matched answer is, if you select the most matched answer, you get 75% accuracy already. We don't know, at least I don't know what exact the solution to jump out or break these cycles, but we believe, and we are also conducting work in self-supervised learning. There's new work that we want to explore self-supervised learning in vision and language tasks to move from dataset to post-dataset to make it dataset agnostic, and adversarial training might also be the way to go. We are seeing difficulties along this line, but my true hope is that with the research progress in adversarial training, we can break this cycle as well as a community. All right, one last teaser that I want to make is we have a new work that is going to appear at ICLR 2020 doing decentralized attribution of generative models. It's nothing related to VNL, but it's an exciting and interesting work that I really want to mention. We can encode and bring and embed keys, and these keys are learned from the data set onto different GANs in a sense that with the generated image, such as the faces, we can reverse attribute which GAN generated this image by using, developing sufficient conditions for model attribution. And we're basically using the keys, and we're showing that the keys are essentially being, if you learn, those keys are clustering at certain areas. That's also an interesting phenomenon we bring to the community as well. With that being said, let me show the overall landscape of the work that we did over the last 10 years, starting from my days at UMD and my days right now at Arizona State, covering visual recognition to robotic space. But in the middle is this work that we want to fill the gap between these two. I would like to acknowledge all the funding resources from National NSF, DARPA, ONR, and all the industrial collaborators. We recently started a collaboration with Samsung Research America as well to do object search in indoor environments. All my current lab members, PhD students, and I do fairly closely collaborating with Chita Barrao's group at ASU on knowledge representation and natural language processing, and Max Iren's group on optimization and machine learning. So what do you perceive from the city of vision and language? Call back the imagined city I mentioned at the very beginning. I think for a CV researcher, you see your own story. For an NLP researcher, you see your own story as well. But since most of the audiences here are machine learning and AI people, I think your belief probably is they are all machine learning carried by machine learning algorithms as well. And then we found final unity. All right, with that, I would like to thank all the audiences, and I'm happy to answer any questions right now, or you would like to have a further discussion, feel free to shoot me an email. We can always organize Zoom meetings since everyone is working from home. And you're also welcome to connect me with on Twitter, and we can have direct interaction over there. Thank you all.
Okay, thank you. We're a little over time, but we maybe have time for a quick question if anybody has one.
I don't know. I didn't got time to check with the chatting, so I don't know whether there's anyone.
I have a question, unless there's one in the chat.
Oh, hey, Stephen.
Go ahead, Stephen.
Okay, thanks for the talk. This is great. So what do you see as the main challenges in visual navigation with language?
That's a great question. I didn't got the chance to talk about. But I didn't see a challenge, but I do see a lot of possible avenues that we can go, right? One avenue that we are also exploring is, I don't know whether you guys are getting into the new data sets such as room-to-room, provided detailed instructions to guide a robot to navigate to a specific location, right? Whenever there is language involved, semantic augmentation can be applied, right? So if you have the understanding of the map through exploration, knowing that the kitchen is opposite of the bathroom, then the instruction saying, go ahead to approach kitchen is equivalent to saying, move away from the bathroom, right? This kind of, that's why I'm trying to say that any VNL tasks, we want to provide a general tool set, and this tool set you can apply, you can even just directly apply onto your new challenge to augment, to make the data more diverse. And in such a case, also, mitigate the risk of sparse reward issue in IL training, right? Mitigate the risk of local minima, stacking in local minima because you don't have a diverse data at the very beginning. And yeah, that's the avenue that I noticed, but I don't know whether it's the big challenge. I don't think it's a big challenge, but I think it's a way we can make it more robust.
Yeah, that makes sense. Thank you.
Okay, well, let's all thank Yezhou again for a great talk. Thank you for joining us.
Thank you for the opportunity again. Really enjoyed the visit. Yes. I really enjoyed it.
Hopefully someday we can make a real visit to Irvine for you too.
Or we can meet somewhere in a real in-person conference, right?
Maybe someday.
Hopefully.